So we're starting up chapter 4, the first section. We talk about antiderivatives and indefinite integration. So really what we want to get to in this section is thinking about reversing the derivative. So we're going to start off thinking about, if I had this, the derivative of a function was 4x cubed, what would the function be? So think about our derivative rules. Pause the video for a second. See if you can figure out what function would give me a derivative of 4x cubed. All right, hopefully you have a few ideas. So any of these would work, right? Any of these original functions, x to the fourth plus 10, x to the fourth minus 72, x to the fourth plus or minus any constant would work here. If you don't believe me, take the derivative of each one of those and see what happens. You'll notice that the derivative of any of those constants is 0, so it doesn't even matter what the constant is when it comes to the derivative. Right, when we find the antiderivative, we call it an indefinite integral. Right, let's take a look at the notation that we have here. So we use this symbol here. This is the integration symbol. It looks kind of like a stretched out S. And in a lot of ways, an integration is a summation, which is kind of where it comes from. We'll talk about that in later sections. The thing that we're taking the antiderivative of, or finding the antiderivative for, is the integrand. So that thing that we're finding the antiderivative of is the integrand. And anytime we have an integral symbol, we pair it up with a dx. Right, so that means we're integrating with respect to x. So it's the x that is considered the variable that's being changed here. And oftentimes when we talk about the antiderivative itself, we use a capital F instead of this lowercase f. And we always have this constant of integration. So we have these bookends around the integrand. That's the thing that we find the antiderivative of. And as soon as we find that antiderivative, the integral and the dx disappear. And we always have a constant of integration that shows up. So take a look at these basic integration rules. There's a long list that you should look over. We need to know these by heart, but in reality you already know these by heart because you know the derivative rules so well that these are just the reverse of them. Notice here, the derivative of sine of x is cosine of x. Derivative of cosine of x with a negative would give me a positive sine x. Derivative of tangent x is secant squared x, and so on. The one that we use a lot for polynomials here, notice we just add 1 to the exponent and divide by the new exponent. And each time we do the indefinite integral, we have a plus c as part of our answer. So be sure to look those over, make sure that you understand those before you go on. So let's look at a few examples. Here's our first example. We want to find the indefinite integral of x squared plus 4x. So this is just a polynomial, so we add 1 to the exponent of x and divide by the new exponent, x cubed over 3. Here we have x squared over 2 with a coefficient of 4. Notice that I've just kept that coefficient and really just dealt with finding the antiderivative of x. That way I'm not trying to find the antiderivative and simplify in the same process, or in the same step. So I have the 4 still there. Antiderivative of x is x squared over 2. Now I can simplify it, rewrite it so it looks better. There's my final answer. All right, so in general, we're going to rewrite the problem, then we're going to integrate or find the antiderivative, then we're going to simplify. When we rewrite, usually rewriting is actually the key step here. We're going to rewrite it so that it looks like the result of taking the derivative. That's what we want to do. We want to make it look like the end result of something after we've taken the derivative of it. So take a look at this example. I have the cube root of x squared. I want to find the antiderivative of that, or I want to find the indefinite integral of that. So I rewrite it as a rational exponent. Now I can just add 1 to the exponent, divide by the new exponent. I'm going to write that down first. Now I can simplify this. If I divide by 5/3, it's like having a coefficient of 3/5. Notice that as soon as I found the antiderivative, the integral and the dx, the integral symbol and the dx disappeared. I had my plus c show up. Next one we have sine x over cosine squared x. I'm going to rewrite it this way. It may not be obvious why I'm doing that yet, but if you look at this, it doesn't look like any kind of end result of a derivative for me. So I'm working toward that here. If you take a look at what I have there, now hopefully it looks familiar. Secant x tangent x is the end result when I take the derivative of secant. So the antiderivative of secant x tangent x is secant x. And as soon as I take that antiderivative, my integral and the dx disappear, the plus c comes in. That's a constant of integration. I don't know what that is because it's an indefinite integral. Last example on this page, we have x cubed plus 3 over x squared. Notice that this integrand has a two-term numerator, but only a single-term denominator. So the first thing I'm going to do is rewrite this x cubed over x squared plus 3 over x squared, separated into two terms. And now I can get just x plus 3 times x to the negative 2. These are just powers of x where I can add 1 to the exponent, divide by the new exponent. Again, notice I have this coefficient of 3. I didn't do anything with that in that first step. I'm just dealing with this x to the negative 2. X to the negative 2, I add 1 to the exponent, I get a negative 1, divide by the new exponent, and then I can simplify that and rewrite it if I want to.